Hey Algebra 2, let's go over the classwork. This is for Unit 4, Lesson 4. All right, today we're still be using that y equals ab to the x formula. All right, but we're also gonna be doing a little bit of exponent rules review because this has an exponent. Our rules for working with exponents, they're gonna apply to that, and it helps us decode and break apart that and make this formula even more useful than it is. Okay, so part of the title here says rational inputs. That means this thing right here is going to be to imagine that this is not just a whole number, but a rational number. That's numbers that are fractions and decimals. All right, and we saw that in the previous lesson, where we could have like a fraction of a decade or a fraction of a week. We're gonna take that even further now. So okay, all right, let's see. You can kind of see the outline of Africa here. That's the next problem that we'll get to. So come on, there we go. Okay, so if we have 5 to what power? 5 to what power is 125? Well, we know that 125 is 5 times 5 times 5, so this power would be a 3. Okay, so what if we had over here, look at this, 1 over 125. Well, that's just putting a 1 over this, and 1 over 5 to what power? Well, 1 over what? This would also still be the same value of a 3. This is leading us somewhere though, because look at now, this is the same. But anytime you have something to a power down here, we can rewrite it as a negative power. So this would be 5 to the negative third power. So let me just write that a little bit bigger. 5 to the negative third power. Anytime you have that, that's equal to 1 over 5 to the third, to the positive third, and that's equal to 1 over 125. So that's how like everything like checks. Now 125 to what power is equal to 5? Well, that's looking at the relationship. What do you have to do to 125 to get 5? Well, you have to take the cube root of 125 in order to get 5. That's what 5 is equal to. But well, what power does that turn into? Do you remember how we did yesterday, how we put a power here and took this? We did it the other way around. Keep the base of 125, but this 3 becomes the base here, and this 1 becomes the numerator, numerators and denominators. So we would get 125 to the 1/3 power. So remember, anything to the 1/3 power is equal to the cube root of something. So if we're trying to find the cube root of this to get to 5, that's why that one works. Okay, all of this is so that we can remember that what do negative powers mean and what do fractional powers mean. We'll be using it. We're going to be working with that. So let's get to the core types of problems here. So we have, here's an interesting thing that I didn't know is that I'm going to show you what I got written on another piece of paper, is that by population, India has the most people in the world. It just finally, past few years or whatever, beat China. They've now got more people in India than all of China. China is way got more people than the United States. And then, with our 350 or so million, there's maybe 100 million less people in Indonesia, and then Pakistan. This list there's like 169 countries here in the world. These are our top 5. Nigeria is the 6th largest country. And its population has been growing. Now, it doesn't look very big, but Africa is gigantic. Nigeria is a big country on its own. So here's the thing, is that there's a lot of people here, and their population has been growing a bit exponentially. In 1990, so I was born in 1980. In 1990, 10 years after I was born, when I was 10 years old, Nigeria had a population of 95 million people. By 2000, 10 years later, 1 decade later, there were about 122. So here, this gives us the amount that it grows by. But here's the thing, they told us in a decade, it increases 28.4% each decade. So let's do it clean. This is what your paper looks like. So what's important? This is our starting value. They're kind of giving us a lot of numbers. That's our starting value in 1990. That's year one. The amount of increase here was from 1990 to 2000. So this was 28.4% per decade. Per 10 years. Per 10 years. So that means our time that we're measuring here is in a decade. That's one, per 1 decade. So 1 decade is equal to 10 out of 10 years. That's what our one whole is. I want to think in fractions like this. So the first thing it says is express the population of Nigeria. We got to write a formula. So the function for every decade is that the population of Nigeria starts with 95.3 million people. We can just write it like that, know that it's millions of people, and it's increasing by 28%. So that's 1.284%. That's what we got to use. We got to take that number. We got to add a 1 onto it because we're increasing that many people. It's increasing. And then we put a D here for the decades. Okay, now remember, this is the number of decades. This now says write a representation of the population in 1996. 1996, that is just 6 years later. That's not even a whole decade. That's 6 years out of 10 years per decade. Look at how I'm making a fraction there. This is how we turn that number, 6 divided by 10, into a decimal, 0.6 of a decade. That's 0.6 of a decade. And we can use either 6/10 or 0.6. Since that's a nice decimal, we're going to use that. So what's our expression for this? Well, it's a 95.3 million people, the same 1.284, but instead of raising it to a power 1 or 2 or 3, it's to the power of, let's do 0.6. Some people like to have that decimal, the extra 0 in front of that when we're expressing decimals, because then it doesn't look like a multiplication sign. So I'll do that. Okay. That's done. We're doing well. A student said the population of Nigeria grew at a rate of 2.84% every year. Explain or show how they're incorrect. Here, let's just say they are wrong. The reason they're wrong is we got to do some math. Oh my God. Here's the thing. This is the growth per decade. Okay, this is the growth per decade. 1.284 is the growth every decade. Okay. 28%, but it's up, this is the growth factor that says how many people you'll have. If we want to find out every 1 year out of every 10 years in a decade, we want to use the power of 1/10. We can use it like that, but 1/10 is also 0.1, so this is the same as 1.284 to the 0.1, 1/10 power, and let's take it. Let's do that. So we've got 1.28 to the power of 0.1, 0.1, and we get this 1.02. 2499, so 245. So this equals 1.025. Look at how that's different. This is different. When we raise this number to that, we're taking like what fraction of this happens per year. This is the total growth factor each year, not each decade. Now that's different than 2.84%. This is, look at that. If we move the decimal over twice and take off the 100%, this is 2.5% growth each, not decade, each year. That's how we figure that out. How did we do that again? We took the growth period per decade and we set the power as a fraction of that decade that we wanted to find. Okay? So that's actually A and B. That's all in one. We just did it all in one. That's the answer to this one. Done. Okay. Yeah, let's move on. This is where you could like pause the video, take a break, but we got this one. Got caffeine. Now, I'm gonna draw like a little graph at the top up here, and I want you to imagine this just goes on. Okay. I'm gonna go 4 evenly spaced things. I'm gonna put a line way up here. This is gonna be 100. Cut it in half. That's 50. Cut it in half. That's 25. And that means right here is 75. Okay. Now, you know, I'm lucky enough where I can just kind of like take a ruler out and use a pencil to graph this. I didn't do this in my other class. This is going to be helpful just to have those gray lines going across. Okay, so that's, so you have a coffee right here. This problem says that that caffeine has an average half-life of 6 hours. It's like one of my all-time favorite problems. So that means, okay, you drink your coffee right here. It has 100 milligrams of caffeine in it. And it takes 6 hours for half of that to get used up. So that means 1, 2, 3, 4, 5, 6. If this is like, okay, whatever, this is 6 hours later, that means that now there's half as much coffee in there. This is one of my favorite problems because I actually want you to imagine here. Imagine that if we just keep going, so you know, keep going with this. If we went another one, so this is 6 hours. 1, 2, 3, 4, 5, 6 hours later, half of that half is left. Now 25% is left, and then you keep going with this another 6 hours. Well, then half of that is left, and half of that is left. And this is what caffeine is, something that gets metabolized relatively quickly. But when people do like illegal drugs and stuff like that, this is like why drug tests work. Is that drugs in your body have a half-life, and they stay in your body because there's this tiny little amount, and you only need that tiny little amount, you know, by the end of the month or so, or after a couple weeks of exposure or use for a work drug test to pick that up. You know, so most of it's gone. The person doesn't feel the effects of the drugs anymore, and a week has gone by. But because it you know, it's only like losing half and half and half and half. There's still trace amounts in the blood. All right. Anyway, with this, this point right here, 6 hours. This is called a half-life. Okay. So what does that mean? That means our amount of time, our one whole time period. One whole time period for our powers and everything is equal to 6 out of 6 hours out of 6 hours. Okay, so if we're going to talk about any other amount of time, any other fraction of time, like 1 hour, that would be 1/6 of a time period. 2 hours would be 2/6 or 1/3 of a time period. 3 hours would be 1/2. 3 out of 6 would be 1/2 of a time period. This tells us what our exponent is. So look at this. This is, all of these are the equations. We would have 100 times 1/2 to the x power, and this is the number of, or maybe h for hours. Okay, and so if we have a 1 here, that means it's not h for hours, it's one set of that time period. That 1 represents one set of 6 hours. And if we look at this next one, the 3, well, that means three sets of 6 hours, which is 18 hours. Okay, and if we look at 1/6, that means 1/6 of a whole 6 hours. What's 1/6 of 6? That's 1 hour. So that is to represent 1 hour. How much caffeine is in the body after 1 hour? We'd only be looking at this one, 1/6 of the way. And so t here, what we are doing is we're doing t, whatever that number is, periods of 6 hours. So that means we're multiplying this times 6. So if it's a whole number like 3, that's 3 sets of 6. Okay, so then we write a function for this, and we kind of already have. I don't know why they're using G. I would want C here for caffeine. But anyway, G of H. And it says G of F represents the amount of caffeine left in the body, H hours. Now, this is not 6 hours anymore. This is every 1 hour becomes the time period. So how the heck do we do that? All right, end of the day, folks. We take that 100 milligrams, we are multiplying it times 1/2, okay? And that's, I'm gonna leave a little space because that is what we would do for just a normal amount of hours, but it's like, how many hours is this? This is 1/6 of an hour. I mean, how many sets? 1/6 of the time period for that half-life. So this would represent each hour, 1/6 per each hour. That's how we do, that's how we write it. So this is our equation. And so since the time period is a 6-hour half-life, and since this 1/2 is based on that, if we're going to express it in the number of hours, we need to take 1/6 of that number of hours. And so here's the thing, we can do one more thing with this. This mathematically can be simplified. We can take 0.5 and raise it to the, I need to use parentheses, 1/6 power. All right, and we're gonna use this. So look at that decimal. That would be the decay rate, 0.89. Instead of 0.5, it would be 0.89 per hour. Instead of 0.5 per 6 hours, that's the amount per hour. So I can take and replace this, keep the H, and rewrite this as 100 times 0.89 to the, so that replaces this. We just did that math. So the only part, so the 100 and the H stay. Maybe I should have done those in blue. The 100 and the H stay, and this part replaces that. All right, last one. So again, this is representing a half-life, and this is representing that there is 89% of the caffeine remains each hour. That means that in 1 hour, 11% is used. I wouldn't say lost, it's used. Your body's doing something with it. Okay, so we took this part and we did this. We simplified with a calculator. All right. Okay, that's it for the core lesson. I'm going to do a separate video going over the homework. All right.